Dear students, last two videos described characteristics of some of the microwave passive devices. Phase shifter is another microwave passive device. A phase shifter is a two-port passive device that changes the phase of an incoming signal. Phase shifters are in the family of time-based effects commonly used on instruments. Phase shifting works by taking the input signal and adding a very small amount of delay to it and then mixing it back with the original signal so that certain frequencies of the audio are in or out of phase with each other. This creates the characteristic sweeping sound of phase shifting processes. The speed and depth of the frequency sweep is usually adjustable. Microwave phase shifters are used in various microwave devices such as systems with a large number of users and in the feeders to radio systems and in phase antenna arrays. Phase shifters can be realized by placing a lossless dielectric slab within a waveguide parallel to and at the position of maximum E field. A differential phase change is produced due to the change of wave velocity through the dielectric slab. The dielectric waveguide phase shifters consist of waveguide sections containing a movable dielectric plate. The phase velocity of the wave and phase shift are affected by the position of the dielectric plate in the waveguide. The dielectric slab tapered at both ends to reduce reflections. Precision phase shifter. Phase shifters are used to change the transmission phase angle of a two-port network. Phase shifters have equal amplitude for all phase states. A precision phase shifter can be designed as a rotary type as shown in figure. This uses a section of circular waveguide containing a lossless dielectric plate length 2L called half-wave section. This section can be rotated over 360 degrees precisely between two sections of circular to rectangular waveguide transitions, each containing lossless dielectric plates of length L called quarter wave sections, oriented at an angle of 45 degrees with respect to the broad wall of the rectangular waveguide ports at the input and output. The half-wave section produces a phase shift equal to twice its rotation angle theta with respect to the quarter wave section. The dielectric plates are tapered through a length of quarter wave length at both ends for reducing reflection due to discontinuity. The resultant field is given by EI e to the power minus j 2 theta into e to the power minus j 4 L beta 1, having the same direction of polarization as the incident field EI with a phase change of 2 theta plus 4 beta 1 L. Since theta can be varied and 4 beta 1 L is fixed at a given frequency and structure, a phase shift of 2 theta can be obtained by rotating the half-wave plate precisely through an angle of theta with respect to the quarter wave plates. Microwave passive devices are used inside microwave measurement instruments. They are used to combine instruments to create more complex measurement systems. In all cases, these devices will split, combine, filter, attenuate, and shift the phase of a microwave signal as it propagates through a particular transmission system. The performance and operation of most microwave objects are commonly described using network parameters determined by measurements or theory or both. Here in this class, I will give information on how network parameters are defined and the properties associated with microwave networks. A microwave network is formed when several microwave devices and components are coupled together by transmission lines or waveguides for the desired transmission of a microwave signal. For a low-frequency network, a port is a pair of terminals, whereas for a microwave network, a port is a reference plane transversed to the length of the microwave transmission line or waveguide. In a low-frequency network, the input and output variables are voltage and current, which can be related in terms of Z parameters, Y parameters, H parameters, and ABCD parameters. A two-port network can be represented by below figure. This is a port 1 and port 2. V1 and V2 are the voltage variables and I1 and I2 are the current variables. Z parameter can be represented by voltage equation. V2 is equal to Z11, Z12, Z21, Z22. I1 and I2. Similarly, Y parameter I1, I2 is determined by current equation Y11, Y12, Y21, Y22. Here V1, V2. For Z parameters, we derive the impedance matrix by selectively stimulating each port with a current source and observing voltage at all ports. Once the impedance matrix is ready, all that has to be done is to multiply it by any new current vector to give us all port voltages. Similarly, for Y parameters, we derive the admittance matrix by selectively simulating each port with a voltage source and observing current at all ports. Once the admittance matrix is ready, all that has to be done is to multiply it by any new voltage vector to give us all port currents. Each of Z and Y parameters could be frequency dependent. H parameters V1 I2 is equal to H11, H12, H21 and H22 and I1 V2. H parameters are useful in describing the input and output characteristics of the circuit. Hybrid parameters use voltage ratio and current ratios to represent the relationship between voltage and current in a two-port network. Now ABCD parameters representing by V1, I1, is equal to A minus B C minus D into V2 multiplied by V2 and I2. ABCD parameters provide the link between the supply and receiving end voltages and currents, considering the circuit elements to be linear in nature. Impedance, admittance, hybrid, and ABCD parameters can be easily measured at low frequencies under short or open circuit conditions and can be used for analyzing the circuit. At microwave frequencies, the voltage and current are difficult to measure because equipment is not available to measure the total voltage and total current at any point. Second reason, over a wide range of frequencies, short and open circuits are difficult to realize, and active devices such as power transistors, tunnel diodes, etc. will become unstable under short or open circuit conditions. At microwave frequencies, the physical length of the component or line is comparable to or much larger than the wavelength. Thus, the voltage and current are not well defined at a given point for a microwave circuit. Therefore, a new representation is needed to overcome these problems at microwave frequencies. The logical variables are traveling waves rather than voltages and currents, and these variables are labeled as scattering or S parameters. S parameters for a two-port network are represented as below figure. S parameters are usually displayed in a matrix format with the number of rows and columns equal to the number of ports. These S parameters can be represented in an equation form related to the traveling waves A1, A2 and B1, B2, where A1, A2 and B1, B2 are the traveling waves, A1, A2 are the incident waves, and B1, B2 are the reflected waves at the respective ports. Therefore, microwave circuits are analyzed using scattering or S parameters, which linearly relate the reflected waves amplitude with those of incident waves. In a reciprocal network, the impedance and the admittance matrices are symmetrical. Proof: consider multiport network. Let Vn plus is incident wave amplitude, Vn minus a reflected wave amplitude. Therefore, total voltage is sum of incident wave amplitude and reflected wave amplitude is equal to 0 at all ports except ith port where fields are EI and HR. Similarly, Vn equal to 0 except jth port where fields are E and H at jth port. As per Lorentz reciprocity theorem, considering a volume containing two sets of sources, ith and jth port, which each produce fields EIHI and EJHJ respectively. From Lorentz reciprocity theorem, where S is the closed surface area of the conducting walls enclosing the junction and N ports in the absence of any source. Since the integral over the perfectly conducting walls vanishes, the only non-zero integrals are those taken over the reference planes of the corresponding ports. So that equation 1 becomes as we know all Vn equal to 0 except Vi and Vj. Equation 2 becomes equation 3 can be read as where Pij represents the power at reference plane I due to an input voltage at plane J. From the admittance matrix representation, I equal to Y parameter into V and power relation V into I. Equation 4 becomes Vi, Vj, Yij is equal to jth port I Yji. Therefore, Yj equal to Yji and Zij equal to Zji. This proves that the impedance and admittance matrices are symmetrical for a reciprocal junction.